Lecture on ML Type Inference. This is video number 6. In this video, we study PTS algorithm for lambda, type unification, and completeness of PTS algorithm. This video is one of the highlights of the lecture. From this video number 6, you will obtain a complete and detailed understanding of a type inference algorithm for the implicitly typed lambda calculus, small lambda. We define the algorithm PTS taking E that infers a principal typing of E, and its detailed proofs of soundness and completeness of this algorithm. So this is the basis of any unification-based type inference systems. On a side comment, this is the Hindley-part of so-called Hindley-Milner type inference. Type inference algorithm PTS for lambda, that is simply typed lambda terms. This algorithm is organized as a recursive function PTS taking just expression and return either a pair of gamma and tau, which is the typing of E, or failure, having the following two properties. First one is soundness. This says if PTS of E returns a typing, then any instance of this returned typing is a derivable typing. So this soundness says that in some sense PTS, this type inference, is correct in the sense that the inferred typing is indeed derivable. The completeness, second property, is the following. If something is derivable under this lambda system, then PTS returns some typing, and this given derivable typing is an instance of the result of this type inference. So completeness say intuitively that this algorithm infer any or possible derivable typing as instances of the result, right? So these two properties establish the following. First one is that the PTS of E, if the PTS of E returns a typing, then this returned typing is a principal typing of E. That is, this returned typing represents the set of all possible typings of E. If PTS return failure, then E has no typing. So this is an obvious correct algorithm. If we can define this PTS with these two properties, then we have completely solved the type inference problem, the third form of type inference problem we have learned in the previous lecture. The definition of PTS. The first part is for cases of these expressions. The idea is to reconstruct a typing derivation tree of E by considering the typing rules. In this case, these three rules corresponding to these term constructors as derivation tree constructors. Right, so let's look at each of them. First one is variable. So PTS of X, you try to return a principal typing of X. In this case, this will do, right? So, and the X colon T for type variable, X has type T. So from this typing, you get any typing of this form, right, by adding extra part of this gamma and instantiating this T for whatever tau, you get this form of typing. Here, in order to do this, you need to use T, fresh type variable T, that is type variable you never used before, right? So this is obviously a principal typing for X. So for X we have done now the constant case. In this case, this is obvious, right? Constant, we don't need any environment, so just return empty environment, and C of B has type B. This is obviously a principal typing of this possible typing specified by const axiom. The third one is lambda x dot E, lambda abstraction. In this case, we recursively call PTS on this body of E to get the principal typing, gamma E and tau E, this pair, and then do case analysis. The first case, if this X is in the domain of the returned type environment, in this case, X is used inside of E, then we eliminate this X part of assumption and return the rest as a type environment. And for type, which is this tau1, which is in this gamma E, so this one corresponds to this tau1, which is a domain part of this function type, and the result part of function type is this type, tau E. So if this is a principal typing, then this is a principal typing for this lambda term, right? There is another case where X is not in the gamma E, that is the principal typing, the type environment part of principal typing of E. In this case, this X colon tau 1 is arbitrary, X is not used inside of E, so X is added to the principal typing of E. In this case, this gamma E is, you return the gamma E itself, and then function type is returning type is this type of E, but domain type is anything, right? Because X is not in the principal typing, so that means X is not used inside of E. So domain part is anything, so we just use fresh type variable t for any representing any type. So in this is the principal typing for this lambda x dot E. Now these three cases, we always succeed, right? There is no failure. And you can see that this is obviously correct, right? The definition of PTS for the case of application term is slightly complicated. And so before giving the definition itself, let's try to analyze the typing rule for function application, that is APP rule. So in view of PTS definition, the rule for application, that is this rule, right? This rule, this familiar application rule, can be regarded as a statement specifying the conditions. The first one is obvious one, that subterms E1 and E2 have principal typings. Otherwise, we have no typing for the entire term, right? So this is obvious one. And then this application rule has this shape, right? This special shape that we have two occurrence of same gamma and two occurrence of tau 1 here and here. This means that this principal typing and this principal typing has respectively instance of this shape and instance of this shape sharing this same type environment, and this same type T1 occurring here and occurring here. This can be specified by this condition. There is some substitution S such that S applied to gamma E1 is a subset of this gamma, and S applied to gamma E2 is a subset of same gamma, and S applied to this result type tau E1 is tau 1 arrow tau 2, and result type of tau E2 is tau 1. There is a condition specified by this application rule. We can regard this typing rule in this way, right? Condition 1 is satisfied by calling PTS recursively, of course. So there is no problem for condition 1. And condition 2 implies that these equations, right? So this gamma E1 and gamma E2 assign the same type to the variable common in both environments. That is this equation and also this equation. So condition 2 implies that there is some substitution S satisfying these two equations, and sufficient condition of these two equations can be represented by the following condition. The system of equations. So there is some S means that so we write down the equation necessary part that so this is the equation that equate two different type. So this is one equation, and this is another equation, which is an equation of two different type. In this case, tau v1 and tau v2 arrow t. T is for anything, so use t as a fresh type variable. So we regard these equation as a system of equation, and then this system of equation has a solution as a substitution, and that solution must be most general one. Then this is a sufficient condition that satisfies the condition 2 specified by this typing rule. So this is the idea of defining the case for function application. Here the important thing is that this second condition can be represented by syntactic system of equations between types, right? So let's look at this in more details. A system of equations represented by some necessary condition specified by typing rule can be solved by the framework called type unification. This is an important building block in type inference. So let's try to look at this type unification and try to understand this type unification. So type unification, the target is type equation. So let E be a set of type equations. Type equations is simply pairs of types. And then a substitution S is called a unifier of E if for each equation in E, this S of tau 1 and S of tau 2 become equal. Right? So this S substitution equate each pair in this set of equations, then S is called a unifier. Right? Then suppose there are two unifiers, S1 and S2. And then we can define a relation on substitutions. S1 is more general than S2. If there is some S3 such that S2 can be obtained by applying or composing S3 with S1, right? So S1 can be specialized to S2. That is one reading of this equation. Then S2 is more specific. S1 is more general, right? So S2 can be obtained by specializing by this substitution to S1. So this is the intuitive meaning of this more general than relation. And then we have a theorem, unification algorithm, theorem of unification algorithm. It says the following. There is an algorithm called U that takes a set E of type equation and returns the most general unifier of E if E has some unifier, and reports failure if E has no unifier. Right? So this is a famous theorem on term unification. This is invented by Alan Robinson for the purpose of automatic theorem proving, and this framework has very general usability so that this can be used to solve any set of type equation if there is some solution. In the next video lecture, we will give a simple and elegant proof of this theorem in the style of Gary and Snyder. from the proof we can extract the algorithm U. So the rest of this video, we assume that there is an algorithm U, given algorithm, and continue to develop PTS algorithm. Right? So we go through in the detail and we show the complete proof of this theorem in the next video. With the preparation we have just done, we can now define the PTS for the case of this application term. Here's a definition, right? We recursively call E1 and E2 and get principal typing for E1 and principal typing for E2. And then make an equation, right? This gamma E1 and gamma E2, the common variable, the type of common variable. So we create an equation for common variable, right? Type of common variable. And also this equation, this type is a function type whose domain type is this E2, and the range type may be anything. So just assume T for fresh type variable. And this equation, and then apply this unification algorithm to this equation to get a solution. And then this solution applied to gamma E1 and gamma E2, the common part is guaranteed to be the same. So apply SE to gamma E1 and apply SE to gamma E2. We can take a union, and the result is a well-defined type environment because common part is the same, and then other part is only belonging to this one and only belonging to this one, and so we can take a union. And then the result of application is this part. So applying this substitution to this type variable, we get a result type. So this is the most complicated part of the PTS algorithm. That is the case for application, but still we can now understand completely that what this algorithm does, right? Well, there is one comment that this PTS may fail because this unification may fail, right? So recursive call of unification may fail. So this may be a failure, this may be a failure, or this unification may be a failure. In that case, entire result is just a failure. So this failure case is implicit. It's not written in this definition, right? If this is a failure, the entire thing is a failure. This is an implicit rule, right? So this is a side comment. Summary of PTS definition. This is the entire type inference definition for untyped, implicitly typed lambda term. So only these 4 cases, and first 3 you always succeed, but this recursive call may fail. So this is a complicated case. We just go through in detail, right? So this is a complete detailed definition of a type inference algorithm that compute a principal typing for any given implicitly typed lambda term. Once we completed the definition of PTS algorithm for implicitly typed lambda terms, then for this simple system, simply typed lambda calculus, we can prove the correctness in detail. The correctness has 2 parts. One is soundness, represented by this theorem. We already stated this property, soundness, but let's go through again. Theorem that if PTS of E returns a typing, then any instance of this returned typing is indeed derivable under this type system small lambda. So here's a proof, right? So first we assume that this PTS returns this typing and take an arbitrary instance, this instance of the returned typing. Then show that this arbitrarily picked typing is derivable. So that part property is by induction on the structure B. Right? So let's go through the induction. First case of variable x. Variable x, we have this typing, and definition is this one. So this is a comment, right? So if E is equal to variable x, then the given instance, this instance must be of this form, because this is the given resulting typing, then any instance must be of this shape. Right? This is by definition obvious. This is an instance of bar axiom. Bar axiom is specified by this way. So this is the instance of bar axiom. So therefore, this instance, arbitrarily picked instance, is indeed derivable. So this is done. Case of constant, right? Constant has this typing rule, and definition of constant case is this one. Now again, any instance, the picked arbitrary instance must be of this form, right? By adding some extra whatever assumption you want to this empty set, and this type is B. So any instance must be of this form, which is just an instance of this constant rule. Therefore, this is derivable. So any picked instance typing is derivable. So we have done. So we have exhausted two cases, and then we have two other cases. Let's go to the other cases. The soundness of PTS for the case of lambda x of E. So in this case, now we use E and E is the same. But now this notation we use according to the definition of PTS, right? So the E is of this shape, right? And this is a comment, right? This is a typing rule for this term, and this is the definition of PTS. And we do reason about this expression, right? So remember that we assumed that PTS succeeds with some typing. So this succeed with some typing. And then we picked the arbitrary instance, and that is the object we are reasoning about now. And then this expression, this definition has a conditional branch according to whether x is in domain of gamma E or not. So there is cases corresponding to this condition, right? So subcase x is in domain of gamma E. Now we reason about the given instance of this one, right, according to the definition. Given instance gamma is a superset of some substitution S applied to this part, that is this one, and tau in the given instance is an application of S to this type. So this is the given assumption. But so we generate gamma with this extension, this new type environment, and then this part x, the assigned type to x is same in this part and this part. So this inclusion is valid, and therefore this typing is an instance of this typing, right? So because this S is a witness to generate from this instance. So this is an instance of this principal typing obtained by this recursive call. But then, because this is a recursive call, by the induction hypothesis, this instance is derivable under this type system. And then by applying the rule abs, we get this typing. But this is the same as tau, so we get this typing. So we have done. So the other case corresponding to this branch, right? This branch. So we reason about the picked instance of this typing. So by definition, there must be some S, such that S applied to gamma E is a subset of this instance gamma, and S applied to this type is tau, right? So this is a given assumption. But since X is not in the domain of gamma E, if we extend gamma with S comma T, this type environment is still a superset of S of gamma E, because this gamma E doesn't contain X, so this addition doesn't matter. So this inclusion is still valid, and therefore this typing is an instance of this typing, principal typing. So by the induction hypothesis, this instance is derivable. So by the rule abs, we get this typing, and this is the same as tau, so therefore this typing is derivable. This is desired result. So we have done both subcase, and therefore this case is proved. The soundness proof of the PTS algorithm for the case of application. This case. So these are comment as before, right? So this term is derived by this typing rule, APP rule, and also principal typing returned by this PTS algorithm is by this procedure, this expression. So we assumed that this expression succeed and return this form of object that is a pair of this environment and this form of type. Right? Before I go into the reasoning about the arbitrary instance of the returned typing, we note that we already noted this, by the way, but we note again that this union is a well-formed type environment, since this SE equate, because this equation, the SE is a result of unification of equation containing this equation, so common part is equal. So this union is a well-formed type environment. This is a comment. Now let's try to reason about the picked arbitrary instance of this typing, principal typing. By the definition, there must be some substitution S that when you apply this environment, we get a subset of this instance gamma, and also S applied to this part, this type part, we get tau. This is a given assumption. Then, so this typing and this typing is an instance of this typing and this typing, right? So by induction hypothesis, right, because this typing and this typing is principal generated by PTS, so therefore by induction hypothesis, instances are derivable. So this is derivable and this is derivable. Right? So far we have two derivable typing, but also this SE is a result of this unification of this equation. The equation contains this equation. Therefore, SE of tau E1 is equal to this part, SE of tau E2 arrow, SE of T. And therefore, this typing is derivable. Right? So this typing is the same as this E1, or this one, right? So by this typing and this typing together, by the rule APP, we get this typing, but this is equal to tau, so we get this typing. So this proves that picked arbitrary instance of this typing is derivable. So this completed the case for this application term, and therefore we exhausted all cases for all expression, and so we have shown in detail the soundness of PTS algorithm. The importance of this type system, I mean the simply typed lambda characters and the type inference algorithm PTS, is that not only soundness but completeness can be shown. And so we go through the detail of completeness theorem, completeness of PTS algorithm, right? So this theorem is this statement we have already shown at the beginning of this video lecture, but let's go through again. Theorem, completeness of PTS algorithm, states the following. If there is some typing of E, derivable typing of E, any derivable typing, then PTS of E succeed with this principal typing, and this derivable typing is an instance of this result of this PTS typing. So this is a theorem, and we are going to show this statement. For this purpose, we assume that some arbitrarily chosen derivable typing, gamma under gamma equal tau, and show that the property, property means this one, this is an instance of the result of PTS by induction on the structure of E, right? So this shows first two cases, variables and constant. For the case of variable x, so this is a comment, right? So x is typing of x is derived by this typing rule, and also the definition of PTS is this one, right? So our job is to show that any given, chosen derivable typing is indeed an instance of this result of PTS algorithm. But in this case, the chosen given typing must be derived by this value, and therefore must be of this form, of this shape. That any of this shape is an instance of this typing, the result of this PTS, right? So we have done for this case. Similarly for this constant case. So this is a comment, right? Constant is derived by, typing of constant is derived by this rule axiom. And the definition of PTS is just this pair. And then given typing, derivable typing, arbitrarily chosen derivable typing, must be of this shape because this is a rule to derive typing. So must be this shape. And this is an instance of this one, right? So we have completed two cases, and two other cases remain. The proof of completeness of PTS for the case of lambda x dot e, this case, right? And then this is a comment that this term, typing of this term, is derived by this typing rule, and the principal typing returned by this PTS is by this operation. So this is a comment. And now we are given a derivable typing of this term, right? We wrote this notation, and this must be derived by this absolute. So this must be of this form because this is a function type. So this must be of this form for some tau 1 and tau 2, such that this is also derivable. Otherwise, this can't be derivable. So the given assumed derivable typing must be this form, and therefore this is also a derivable typing of E. Because E has derivable typing, then by induction hypothesis, PTS of E succeed with some principal typing such that this is an instance of this one, right? So by the definition of instance, there is some substitution such that S applied to gamma E is a subset of this one, and S applied to tau E is equal to tau 2. So far we have obtained this, and then we do case analysis that whether the returned, so evaluation is this branch or this branch, right? So subcase that X is in the domain of gamma E, right? In this case, S applied to this gamma E excluded by the this assumption of X is subset of gamma, and this is tau 1. So in this subcase, this is an instance of this typing, this typing, right? So we have done this subcase. The other subcase, X is not in the domain of gamma E. In this case, we make another substitution by composing this T is mapped to tau 1, and this one-point substitution composed with given S. Then S prime applied to gamma V is a subset of gamma, right? Because this doesn't contain X, so the result of this gamma S doesn't matter, and this still holds. And S of T is tau 1, right? We have this one, therefore this typing is an instance of this, instance of this, and we have done for this subcase also, and we have completed the case of this lambda x dot E. The proof of completeness of PTS for the case of application. This case, and again, these two are comment, right, to proceed to write down the proof, right? So this typing of this term is derived by this APP rule, and the result of PTS algorithm for this term is by evaluating this expression, right? Then we need to show that given derivable typing for E1, E2 is an instance of a principal typing returned by this expression. That is our obligation. So we first need to show that this succeeds with some principal typing. Now, so we start reasoning about the given derivable typing. So derivable typing must be derived by this APP rule, right? So by this APP rule, there must be some tau 1 such that this typing and this typing are derivable for some tau 1, right? So by the induction hypothesis, this recursive call and this recursive call succeed with some typing, some principal typing of this and this. So by induction hypothesis applied to E1, we get this result. PTS of E1 succeed with this principal typing, and this derivable typing is an instance of this one, right? Same as PTS of E2. So PTS of E2 succeed with some principal typing, and this derivable typing is an instance of this one, right? So far we are given by the induction hypothesis, right? Then by definition of instance of relation, there are some S1 and S2 such that S1 applied to this gamma E1 is a subset of gamma, and S1 applied to this tau E1 is tau 1 arrow tau. Similarly for E2, so S2 applied to gamma E2 is a subset of same gamma, and S2 applied to tau E2 is tau 1, right? So far we have obtained these results by induction hypothesis and by the definition of instance relation. we now reason about the type inference algorithm. This PTS algorithm is constructed in such a way that each time we introduce type variable, those introduced type variables are always fresh, never used before. So by this property, this substitution that create an instance, and this substitute type variable returned by this E1, and this substitute type variable returned by this PTS E2. So we can assume that this domain of S1 and domain of S2 are disjoint, and also this T introduced by this branch is not in either domain of S1 or domain of S2. We can also assume this property. Then we generate new substitution by composing this one-point substitution. T maps to tau. This is a given instance tau, and compose this one-point substitution with composition of S2 and S1. Then, because of this property, S applied to gamma E1 is still a subset of gamma, same as S applied to gamma E2. And S applied to tau E1 is same as S applied to tau E2 arrow T. And therefore, S is a unifier of E, right? E, this equation, right? S equate these equation and these equation. So by the unification theorem, there must be some S prime such that S can be represented by the composition of S prime and SE, this SE. Then S prime applied to this one, this returned type environment, is a subset of the given gamma in the given derived typing. And S prime applied to this SE of tau E1. Tau E1 is this one, this type, is equal to this S prime applied to SE of type tau E2 arrow S prime applied to SE of T, right? Because of this equation. That is the type tau1 arrow tau. So this property is obtained, and therefore this is an instance, this typing. This is a given arbitrarily chosen derivable typing is an instance of instance of this result of the algorithm, in this case of this application. So we have completed, this is a little bit complicated, but nothing magical, nothing difficult part exists, and so we just go through every detail, and we have completed successfully for this case. And therefore we completed the entire proof of completeness of PTS algorithm. So far we have completed the proof of completeness, and therefore that is the contents of today's lecture. Here is some supplemental comment. First one is constructive proof. Some comment on constructive proof. Constructive means that there is some property that we wanted to have some value satisfying some certain property. This is often the case for computer science programming language. So typical statement looks like this one. This is abstract notation. Well, let's look at some example. Any type correct expression E has a principal typing, right? So this expression, in order to show this expression, right? So this is abstractly written in this form. For any element of this inductive closure, there is some value satisfying this property, right? So this is a typical statement we wanted to prove, often the case for this kind of proof. And the way we do this is the following. We define a function phi that returns the desired value with a proof, both with a value and proof by induction on this inductive closure. For constant, we directly define value and prove the property. For constructed element, we define from this application of this phi to component, and corresponding to this syntactic constructor, we define how to construct a semantic object and assume that each component satisfies some desired property and show the constructed element has the desired property. This is a typical shape of proof, and in this example, any type correct expression E has a principal typing. This we have just proved by defining this PTS algorithm, and PTS algorithm does construct some value, in this case principal typing, and then for each case the principal typing has desired property. So this is a comment that the typical proof structure often used. So this is just a comment. In the previous video, we gave small exercise about sorted inductive closure, so we gave some sample solution, right? So one exercise is this one. Verify this equation. So this is a generalization of inductive closure to sorted inductive closure. So now this script set is sorted set, and we claimed that this is defined to be the smallest set containing C and closed under F. These notions are generalized to sorted set, and then this big intersection is also the big intersection of sorted set, right? And this proof can be just mechanically transformed from the conventional, standard definition of inductive closure to sorted inductive closure. Just mechanically transformed. So you can check this, right? So proof. This is a sample proof. Let delta to be this set, this set, right? Then, since the universal sorted set contains C and closed under F by definition, so this delta contains this set, and therefore this is not empty. Now we pick arbitrary element from this set, and then this element has this shape, this sorted function. Then according to this sigma 1 through sigma n, we pick tuple of this n tuple from this big intersection. We pick arbitrary element, and also let V, this is a sorted set, to be arbitrary element of this delta. And then this V, because this V is from this delta, so this V is closed under F. So this picked tuple is also in this V, right? Then application of this is in this V dot sigma. Since V is arbitrary, this implies that this result is in the intersection, because this result is in every set V, so in the intersection. So this shows that this big intersection is closed under F, because this is the smallest set. Therefore, this equation holds. This is exactly the same as the standard definition of inductive closure. I also gave an exercise that asks you to show this equation. This is a generalization, the same equation, but C, F, and X are generalized to sorted set. So, right? So Again, this proof is mechanically transformed from the proof of standard definition of inductive closure, right? So you can stop the video and go through. So therefore, it's isomorphic state step by step. So nothing complicated. So that the generalization of inductive closure to sorted inductive closure is indeed just a smooth and simple and systematic generalization, right? So nothing complicated. I skip the detailed reading of this proof. This is the final slide of today's lecture. Lecture of this video number 6. I gave an exercise about typing derivation with ABS, absolute, and this is a sample exercise solution. The exercise is this one. I said recommended for all the audience. Content is that check the following is a valid derivation tree according to the definition. So this is this tree. So only strange looking part is this part that you keep this type environment. And the conclusion, x colon tau is not eliminated, right? Otherwise, this is just a straightforward application, right? This APP is just a standard application. So we check that this is okay, right? So by definition, this notation is defined to be the equal to this one, right? So this is by definition. And therefore, this notation is the same. This denotes the same tree as this notation, because this is same as this one. And this application is a valid application of absolute. So therefore, this is a valid application. So this is valid derivation tree according to the definition, right? So you notice that this property we used to show the soundness and completeness of PTS algorithm, right? So therefore, this is a very good exercise you wanted to try, right? So this is just a sampling solution. Now this is the end of the entire lecture video number 6.